Okay class, let's have another problem. A 2-meter cantilever beam carries a uniformly distributed live load of 8 kN per meter and a dead load of 12 kN per meter, including its self-weight. Its self-weight is the weight of the beam on its entire span. A concentrated live load of 20 kN and the dead load of 10 are also applied at the free end of the beam. So that is the concentrated load P. Using Fc prime, that is the cylinder strength of concrete, which is 25 megapascal, and Fs, that is the allowable tensile stress of steel, which is 138 megapascal, and then N, the modular ratio, which is 10, and the base is D over 2. You have your D. And then the cover for this beam is 60 millimeter, and we will use the 25 millimeter diameter to design the beam. Okay, so let's have the solution. You have to solve for the total load, for the concentrated load, and the weight W, or the distributed load. So for the load P, you are given a live load and a dead load. So you have P for dead load, which is 10, and P for live load, which is 20. So all in all, you have your concentrated load P equal to 30 kilonewton. And then for the W, which is the distributed load, we also have the W, or the distributed load, for dead load and for live load. So for dead load, you have 12. For live load, you have 8. So all in all, you have the distributed load equal to 20 kilonewton per meter. And then we will solve for the maximum applied moment. So you can solve for the maximum applied moment using shear and moment diagram. Okay, using shear and moment diagram, you have the shear, and then you have the moment. I think that's one. Okay, so you can solve for the maximum applied moment using shear and moment diagram, or you can have the notes. I already assigned to you the maximum moment for cantilever beam. Okay, for the load W, you have your maximum moment equal to WL squared over 2. And then for load P, which is at the free end, that is P times L. So we have W and load P, so let's add the moments. So for the applied moment, for the load W, you have WL over 2. Then for the load P, you have P times L. So substitute the values. You have for load W, that is 20 times the length, which is 2, raised power of 2, that is squared, over 2, plus 30, which is the load, concentrated load P, multiplied by the length of 2. So you now have your moment, applied moment, equal to 100 kilonewton meter. So your applied moment, it should be converted into Newton millimeter. So to convert it, you have kilonewton meter multiplied by 1 meter, 1000 millimeter, and then for kilonewton, that is 1000 newton over 1 kilonewton. So that is, so cancel, and then cancel. So that is Newton millimeter. So 1000 times 1000, that is 1 million. So to convert that into scientific number, that is 10 or times 10 power of 6. You have 6 zeros, so 6. Okay? So for the resisting moment, I already gave you the formula for the resisting moment for concrete and also for steel. So for concrete, you have the formula 1/2 FC K G B D squared. Okay, we have our MC equal to MA, so that we'll have the safe load. So MC is equal to MA, which is equal to 100 times 10 to the power of 6. We already convert that to Newton millimeter. And then FC, given in the formula, that is 0.45 of FC prime. We have our FC prime equal to 25, so 0.45 times 25 is equal to 11.25. That is in megapascal. So to convert megapascal into Newton per meter squared, so that is just equal megapascal and Newton per meter squared. And then we also have our B, which is D over 2. And then in design, you have your K, and also for investigation, you have another formula for K. But this is design problem, so our K is equal to N over N plus Fs over Fc. Okay? So that is equal to 10, which is the modular ratio given in the problem, divided by 10 plus 138 over the FC, which is 11.25. So now we have our K equal to 0.45. And then we will solve for J, that is equal to 1 minus K over 3. So I already gave you these formulas. Okay. So for J, that is equal to 0.85. To continue, we'll substitute all the values. So you have for MC, that is MA or equal to 100 times 10 to the power of 6. Okay. And then equal to 1/2. Then FC is 11.25. K is 0.45. J is 0.85. Your B is D over 2, and you have D raised to the power 2. So you have D squared and D, so D cube, or you just have the cube root of 4 times 100 times 10 power of 6 divided by 11.25 times 0.45 times 0.85 in millimeter cube. So now you have your D equal to 452.99, or you just round it up to 453. And then to solve for B, given B is equal to D over 2, so we have already solved the D. So 453 divided by 2, that is equal to 226.5, or that, let's round it up to 227 millimeter. So that's for concrete, to solve for B and D. To solve for the number of bar, we will have the steel resisting moment. Okay, so the formula for resisting moment of steel is MS equal to AS FSJD. So let's also equate our MS equal to MA, which is equal to 100 times 10 power of 6 Newton millimeter. And then our FS given, that is 138. And then J, you have 0.85. We already compute J. Then D is 453, this one. So substitute the values. You have MS, which is equal to 100 times 10 power of 6. And then you have to solve for AS. FS is 138. J is 0.85 and D is 453. So you have your AS equal, or area of steel equal to 1,888.93. So this is the required total area of steel. Okay, and in the problem, we are to use 25 mm diameter. So we'll have to solve the number of bars. So the formula for the number of bars, you have the AS, or the required total area of steel, divided by the area of one bar. So we'll use 25 for our bar diameter. So you have 1,881.93 divided by pi over 4 times 25 squared. So your number of bars is 3.8, but you cannot put 0.8 in the beam, so round it up always to whole number, even if that's 3.1. So round it up also to 4. Okay, so you draw the section and the positioning of your rebar. So for the spacing of rebars, you have this formula depending on the number of spacing. So for the minimum side cover, we will use the 40 millimeter. So based on the code, you have the 40 millimeter side cover. And then you have the diameter of the bar and the spacing of the rebars. You also have the cover for your reinforcing bars, and you solve the D. So to solve for the spacing, you have the formula B, or the base, is equal to 40 times 2, that is the side cover, plus 4 times the bar diameter, so 4 bar diameters, plus 3 times the spacing, 3 spaces or 3 spacing. So B is 227 is equal to 40 times 2 is the side cover, then 4 times 25, that is the bar diameter, plus 3 SB or spacing. So you have your SB equal to 15. But in the NECP code, you have to follow the minimum spacing. Okay? It should be that your spacing is greater than or equal to 25 mm, and spacing should be greater than the bar diameter or equal to, and also spacing should be greater than 1 1/3 times the maximum size of aggregates. So usually size of aggregates, that is 1/4 or 3/4 depending on the specs. Okay, but we have the spacing equal to 15. So you check, you have the spacing 15.7, that is less than 25, so not okay. And also 15.7 is less than the bar diameter, that is 25, so not okay. So we'll have the repositioning of, or the another arrangement of our rebar. This one. This is now your spacing. Then you have 40 cover. So to solve for the spacing, you have B is equal to 2 times 40 plus 2 times the bar diameter plus SB. You only have one spacing. So therefore, you have 227 is equal to 80 plus 50 plus SB. So you have your SB equal to, so it should be greater than 25. So this is now the positioning of our, or arrangement of our rebar. So therefore, our rebar should be placed by bundles or by or in 2 layers. Okay, so that's all. Thank you.